Hi Year 11, welcome to a series of videos on the topic of differentiation, and this is for the Mathematics Analysis and Approaches course for the International Baccalaureate. So we're going to begin with Introduction to Differentiation. So here's our topic outline. After we've covered Introduction to Differentiation, we're going to look at the rules of differentiation, and then we're going to learn to differentiate log and exponential functions, trig and inverse trig functions. Then we're going to look back at some of the fundamentals of calculus with further limits. We'll look at properties of curves, optimization, rates of change, and then we'll finish off with kinematics. So let's start with the definition of a limit. In mathematical terms, the limit is the value that a function approaches but cannot exceed. Think of it as a ceiling or a brick wall. And we've seen this concept before with asymptotes. We use the following notation. This says the limit as x approaches 2 of some function x plus 5. And we can see here that as we are getting closer and closer to x is equal to 2 from either direction, then the function value is getting closer and closer to 7. And all we do is substitute the 2 in where the x is. Let's find the limit as x approaches 2 of x squared minus 4 all over x minus 2. So what happens if we substitute the 2 in? On the numerator we're going to get 2 squared minus 4, which is 0. And on the denominator we're going to get 2 minus 2, which is also 0. Now 0 divided by 0 is undefined. But luckily we can do something sneaky here. We can factorize the numerator. It's a difference of 2 squares, and those x minus 2's are going to cancel out. So this question is reduced to, what is the limit as x approaches 2 of x plus 2, which of course is 4. Now graphically, this function looks like this. It's actually a straight line, y equals x plus 2, but it has a hole here because x can never equal 2. We can't have 0 in the denominator. You can see that the limit, as we're getting closer and closer to 2 from both sides, it's approaching 4. Which brings us to a really interesting question. How do we know if a limit exists? Now there's a really simple definition, and it goes like this. If from the left we are approaching the same limit that we approached from the right, and that limit is a real number, then the limit exists. This is how we write it. The limit as x approaches a from the negative side of f of x must be equal to the limit as x approaches a from the positive side of f of x, and they both have to equal k, and k has to be a real number. It can't be infinity. So here's a famous mathematical joke. An infinite number of mathematicians walk into a bar. The first one orders a beer, the second one orders half a beer, the third one orders a quarter of a beer, and the barman says, "You're all idiots," and pours 2 beers. Now that scenario is exactly the limit of the series 1 plus a half plus a quarter plus an eighth, etc., etc. And it looks like this. Here's the first beer, here's half a beer, there's a quarter, there's an eighth, there's a 16th. Now suppose we take the limit of that series, we go all the way to infinity. What do you imagine the limit is? Now what we've actually got here is a geometric series. And if we look at the sum of n terms, u1 is equal to 1, r is equal to a half, and we're just going to let n equal n. Substituting that in, we end up with this. Now on that denominator I've got 1 take away a half, which is a half, so I can simplify this. So the sum of n terms is 2 multiplied by 1 minus a half all to the power of n. And so the sum to infinity of this series is going to be the same as the limit as n approaches infinity of the sum of n terms. Now, we don't ever substitute in infinity for n. But as n tends towards infinity, this here is going to equal 0, and I'm going to show you why. This is actually equivalent to 1 to the power of n over 2 to the power of n. And 1 to the power of anything, of course, is 1. All right, if we think about as n approaches infinity, 2 to the power of n, so 2 to the power of infinity, is infinity. So I've got 1 divided by infinity there. And that, of course, is 0. And 2 multiplied by 1 is 2. So the limit of this is 2. So hopefully you've got the concept of a limit. Let's change tack. Let's talk about gradient. Recall we can calculate the gradient of a line through 2 points, A and B, using the formula shown. Now here we have a secant, that's the name of this blue line. It cuts this parabola in 2 points. And if I substitute those points in, the gradient of that secant is 3. Now the question is, what happens to the gradient of that secant as we slide this point down the black curve closer and closer to the point 1, 1? In other words, as the secant becomes a tangent. Let's do a quick demonstration on Desmos. So here we have got the gradient of the secant, and as we pull that point down the curve closer and closer to the point 1, 1, you can see how the gradient is decreasing. When it gets to the point 1, 1 and we have the tangent, the gradient is undefined. So here's a table of those gradients. You can see the points getting closer and closer to the point 1, 1, and the gradient is decreasing. So what do you imagine is the gradient of the tangent through 1, 1? Of course, here we're talking about the limit, aren't we? A reasonable guess is 2. Okay, let's get into the formal theory. We're going to choose 2 points, x and f of x, which is down here, and then x plus h and f of x plus h. And h is a small number. The gradient of the line between the 2 points is going to be the difference in the y values over the difference in the x values. And we can tidy up this denominator. So there's the gradient of the line between those 2 points. And so to find the gradient of the tangent, we calculate the limit as h tends to 0 of the gradient function. Now when we find the derivative, we say we are differentiating y, which is the function, with respect to x. And there are a couple of different notations. We can write y with an apostrophe after it, and we say y dashed. Or we can say f dashed of x. Or we can say dy dx. And this comes from delta y over delta x, which means how is y changing as x is changing? So let's have a look at how we might use this. We're going to calculate the derivative of f of x is equal to x squared minus 3x plus 5, and we're going to do it from first principles. So we're going to use this formula. We'll start by substituting in f of x plus h and f of x. And be careful to put f of x in brackets because there's more than one term. All right, let's expand all of that out. Now you can see that we've got some x squareds that are going to cancel, and some 3x's and some 5's. And we're left with the limit as h approaches 0 of 2xh plus h squared minus 3h all over h. And we can factorise an h on the numerator. These will cancel, and so this question reduces to what is the limit as h approaches 0 of 2x plus h minus 3. And when we substitute the 0 in here, we're going to end up with 2x minus 3. So that's the derivative of x squared minus 3x plus 5. And this is the gradient of all the tangents to the curve f of x equals x squared minus 3x plus 5. Now it is quite onerous to differentiate through first principles, so I'm going to show you some common derivatives and then show you a shortcut. So if we've got y is equal to x squared, then the derivative is 2x. For x cubed, the derivative is 3x squared. For x to the power of 4, it is 4x cubed, and I'm sure you can see the pattern. X to the power of 5, the derivative is 5x to the power of 4, and for x to the power of 6, it is 6x to the power of 5. And this is the power rule. If y is equal to x to the power of n, then to find the derivative, we bring the power down the front, x, and then reduce the power by 1. So the derivative is y dashed is equal to nx to the n minus 1. And so that brings us to some simple rules of differentiation. Number 1, any coefficient of x will be multiplied by the power when it comes down the front. So here's an example, differentiate 6x cubed. So when we bring the 3 down, it's going to multiply by the 6. And so our answer is 18x squared. Now have a look what I've done here. This means find the derivative with respect to x of 6x cubed. It's the same as dy dx, but this is y. Number 2, we differentiate term by term. Here's an example, find f dashed of x if f of x is equal to 3x to the power of 5 minus 2x cubed plus 6x squared. So our derivative is going to be, bring the 5 down, it's going to multiply by the 3, so that's 15x to the power of 4. Take away, bring the 3 down, 3 2s are 6x squared plus, bring the 2 down, 12x. There's our derivative. Number 3, the derivative of ax is a. And here I'm talking about x to the power of 1. Let's have a look at that. So let's find the derivative of y is equal to 6x. Now that's actually the same as 6x to the power of 1. And when the 1 comes down, I'm going to get 6 times 1 is 6, x to the 0. And of course we know x to the power of 0 is 1. So effectively, the x just disappears. Number 4, the derivative of a constant term is 0. Again, let's check this out. Let's differentiate y is equal to 3. That's a constant term. Now that's the same as 3x to the 0. What happens when we bring the power down? 3 times 0 is 0. It wipes the whole thing out. Can you see that? Doesn't matter that the power drops to -1. And that's it for our simple rules. So let's look at some examples. Find the derivative of y is equal to 3x to the power of 5 plus 2x minus 17. Our derivative will be, bring the 5 down and multiply by the 3, 15x to the power of 4 plus 2. How about this one? F of x is equal to -3 x to the power of 4 plus x over 4. So our 4 comes down, gives us 12x cubed. What about this? That's the same as 1/4 x. So when we have a coefficient in front of an x to the power of 1 and we differentiate, we're just left with the coefficient. So f dashed of x in this case is -12x cubed plus 1/4. Now what about negative powers? We can differentiate negative powers using the same method. So if we've got y is equal to x to the power of -3, the -3 comes down, x, and then we drop this power by 1, so it becomes -4. What about f of x is equal to 4 over x? We can't do anything in this form. We need to turn this into index form, which is 4x to the -1. Now we can differentiate. -1 comes down, multiplies by the 4, x, drop the power by 1, becomes -2. So the derivative is -4x to the -2. Fractional indices are fine as well. Let's differentiate f of x is equal to 2x to the power of 1/3. So the 1/3 comes down and multiplies by the 2, x, and then subtract 1 from this power. So f dashed of x is equal to 2 times 1/3 x to the power of negative 2/3. Here's another example. Differentiate f of x is equal to the square root of x. Now, the same as for our question we did with negative indices, we can't do anything in that form. We need to change it to index form. Now we can differentiate. The half comes down, x to the power of negative 1/2. Now you can leave it in index form, or you can change it back to radical form, 1 over 2 root x. Now let's quickly look at brackets and quotients. If we want to differentiate expressions inside brackets, we have to expand them first. So let's differentiate y is equal to x minus 2 in brackets multiplied by 3x squared minus 7. Just using FOIL, y is equal to 3x cubed, take 7x, take 6x squared plus 14. And differentiating term by term, we end up with 9x squared, take away 7, take away 12x. Now we are going to be learning a method called the product rule, which will help us differentiate products in brackets. And quotients. Suppose we want to differentiate f of x is equal to 3x minus x squared all over 4x. Now this is a top-heavy fraction, so we can split it into 2. It's going to become 3x over 4x, take away x squared over 4x, which simplifies to 3/4 take away x over 4, and now we can differentiate term by term. And so f dashed of x is going to be 0 take away 1/4. It's negative 1/4. Now hopefully you're thinking, well, what if it's not a top-heavy fraction? What if it's a bottom-heavy fraction? And we can't actually do this question at this point, but we are going to be learning a method called the quotient rule, which will help us differentiate quotients. Now, differentiation is not only restricted to y and x. There are many other quantities that we can and do differentiate. And I'm just going to show you a cool example of this. This is the volume of a sphere, 4/3 pi r cubed. And we can differentiate volume with respect to radius. So we can work out dv dr. Now, you might be a bit confused here. We can only differentiate with respect to one variable, and in this case it's r. Pi is not a variable, it's a constant. So if we want to work out dv dr, the 3 comes down and multiplies by the 4/3 pi, and then we end up with r squared. So dv dr is equal to 4/3 times 3 pi r squared. And when we tidy that up, lo and behold, we end up with the surface area of a sphere. How amazing is that? Let's think about it. Suppose we have a sphere, and suppose that the radius is increasing. Then the rate of change of volume as radius increases is surface area. It's kind of like we're painting an extra layer on. And another common application is kinematics. It's really important in physics. It's where we consider a particle moving along a line, and x of t describes the displacement of the particle at time t. Well, the first derivative, dx dt, is the velocity of the particle at time t. It's how displacement is changing as time changes. And the second derivative, which is written like this, is the acceleration of the particle at time t. And we're going to do a whole lesson on this. Now we've learnt how to differentiate, but what does it all mean? Let's summarize. The derivative finds the instantaneous rate at which some quantity is changing in relation to another changing quantity. And in this video we've looked at how is y changing as x is changing, so dy dx. We've also looked at how is volume changing as radius is changing, and how is displacement changing as time is changing. And so that's it for this lesson. In our next lesson, we're going to look at rules of differentiation.